Okay, so we'll start off by doing problems from chapter 5. So this problem says to start a car engine, the car battery moves 3.75 times 10 to the 21 electrons. You see, this is about 100th of a mole. This is less than a mole. Electrons through the starter motor. How many coulombs or charge were moved? Okay. So the charge of an electron is 1.6 times 10 to the minus 19 coulombs. Okay, so this is something you can look up on the web, but it's also on your notes. Okay, so the total charge is the number of electrons moved times the charge of each electron. So that's so about 600 coulombs of charge were moved through your starter motor to get your car started. All right, to put this into perspective, a large thundercloud, the charge is about 60 coulombs. So to get your car started, there's 10 thunderclouds worth of charge that was moved. Yeah. All right, suppose a speck of dust in an electrostatic precipitator has 10 to the power of 12 protons. Okay, so a trillion protons in it, and has a net charge of minus 5 nanocoulomb, a very large charge for a small speck. Okay, so to remove this dust, you have to put that much charge in it. So it costs you a bit of money. Okay, like I said, 1 to 2% of the electricity produced. Okay. How many electrons does this have? So has a net charge of that. Okay, so if it has that many protons, it has to have that many electrons to be a neutral particle. And then on top of that, it has enough electrons for that much charge. Okay, so let's calculate this. Okay, so the number of extra electrons equal to charge divided by the charge of the electron. So I guess I'll put nanocoulomb. And the charge of an electron is 1.6 times 10 to the minus 19 coulomb. Okay. So the number of electrons is, you have to neutralize that charge plus this charge. Okay. So 10 to the power 12 plus 0.0312 into 10 to the power 12. This number is that. Okay, the reason I wrote that is you had to increase the number of electrons by 3%. And that's a very hard task to do. Okay? So it would be almost impossible to put 3% more electrons in your body. Okay? But anyway, it's a small speck, so you're able to do that. All right, what net charge would you place on a 100-gram piece of sulfur if you put an extra electron on 1 in a trillion of its atoms? Okay, now this is this is sort of a more feasible thing. So for every trillion sulfur atom, you're going to put an extra electron. Yeah. So let's calculate how many sulfur atoms there are in this 100-gram piece of sulfur first. You know. How do we calculate this? What is the atomic weight of sulfur? Okay. So 32 grams, okay? So 32 grams of sulfur has how many atoms of sulfur? 1 mole, very good, okay? So the number of sulfur atoms is 100 grams divided by 32 grams per mole, and then times 6.023 times 10 to the 23 per mole. Okay. Atoms per mole. Okay. So this is so the number of sulfur atoms you have is 2 times 10 to the power of 24 in 100 grams of sulfur. Okay? So the number of electrons you're going to put is 1.9 times 10 to the 24. For every trillion atoms, you're going to put that. So 1.9 into 10 to the power of 12 electrons is what you're going to put on this 100-gram piece of sulfur. Okay. Protons in an atomic nucleus are typically 10 to the minus 15 meters apart. What is the electric force of repulsion between nuclear protons? Okay. Okay, I'm going to extend this problem because I just thought of something. Well, it'll be interesting to see. All right. So the force of repulsion is K Q1 Q2 divided by R square. What is the charge on the proton? The charge on the proton is the same as the charge on the electron. Okay, and K is 9 times 10 to the 9 Newton meter square by Coulomb square. 1.6 times 10 to the minus 19 Coulomb square. And this is 10 to the minus 15 square meter. Okay. All right, so we want to take care of the powers of 10 first. That's 10 to the power of minus 38, and that's minus 29. That's minus 30. So 10 to the power 1. So 9 times 1.6 square, 90 times 10, 1.6 square. Did I do that right? So 90 times 1.6 square. That's the force between these protons. $230 newtons. Okay, that's so the repulsive force between these two tiny particles is roughly half your body weight. Okay, so that's pretty strong. All right, let's do the following. We'll calculate the potential energy between these two guys. Okay, and you'll see in a second why I'm doing this. Okay, so the potential energy is K Q1 Q2 divided by R. So it's just 4 times, we'll multiply this force times R. Okay, so it's equal to 230 Newton times 10 to the minus 15 meters equal to, so, and that'll 2.3 into 10 to the minus 13 joules. So that is the potential energy between these two guys. All right, what does the sun do? How does the sun produce? How does the sun produce energy? Okay. It has to be roughly 10 to the power of half of this, 10 to the minus 13 joules. Okay, and the kinetic energy is related to the temperature by 3/2 kT. Okay, so if the sun's temperature is that, see this simple problem and you're able to calculate the temperature. Okay. All right, do you guys understand what's going on? All right, so let's calculate the temperature. And then you'll see a surprising thing, okay? 2/3 10 to the minus 13 joules divided by K. What is K? K is the Boltzmann's constant, okay? So 2/3 10 to the minus 13 joules divided by, and you can look up Boltzmann's constant. Somebody was mentioning this, joules per Kelvin. All right, so this is, okay, 10 to the power 10 Kelvin, 10 to the power 10, and then we'll do this 2 divided by so the temperature of the proton combining is 4.5 billion kelvins. But let me remind you something. The temperature in the center of the sun is 15 million Kelvin. 100 times colder than that. So how the heck is the sun, how the heck are fusion reaction happening? You guys understand the problem? All right, so this is where the Maxwell-Boltzmann's distribution comes in. See, the probability of a particle having this speed is like that at any given temperature. And only these protons are going fast enough to fuse. Okay? All right, so that's what's happening. All right, anyway. All right, the next problem is 2 small balls, each of mass 5 grams, are attached to silk threads 50 centimeters long, which are in turn tied to the same point on the ceiling. Okay, I don't have the diagram. When the balls are given the same charge Q, the thread hangs at 5 degrees to the vertical as shown. What is the magnitude of Q? All right, so okay, so that is 5 degrees. This is 0.5 meters. And what we'll calculate is we'll have to calculate R. Okay, so now let me draw just one guy. The forces on These guys are the electrostatic force. So the force on this one guy is these three: the tension in the string, the repulsive force, and the weight. And since this guy is at rest, he's in equilibrium, the sum of these three forces is zero. Okay? This angle is 5 degrees. This angle is 5 degrees. Okay, now before we do anything, let's calculate R. So tan 5 is R by 2 divided by 0.5 meters. So R is equal to tan 5. R is 0.087 meters. All right, so now from this diagram, T cosine phi is equal to mg. And T sine phi is equal to this force, is balancing that, equal to Fe, which is K Q square divided by R square. So let's say this is equation 2, this is equation 1. 2 divided by 1 gives you tan phi equal to KQ square by R square divided by mg. What is it that we're looking for? Q. So let's solve for Q. Okay. So Q square is mg R square tan phi divided by K. Okay. All right, now we can put in stuff. What is the mass? It's 5 grams. Kg is 9.8 meters per second square. Tan 5 is 0.087. K is 9 times 10 to the 9. And R is 0.087. And this will all work out in coulombs. Okay, so this is 10 to the minus 12. Square root of that will become 10 to the minus 6. Okay. Okay, so we get 0.06, okay, or 60 into 10 to the minus 9 coulombs. 60 nanocoulombs. Okay. So the charge on each of those pairs is 60 nanocoulombs. On a typical clear day, the atmospheric electric field points downwards and has a magnitude of 100 Newton per coulomb. So the electric field is pointing down this way. And you will learn in one of the next chapters that 100 Newton per coulomb is equal to volt per meter. So every meter, there's a 100-volt difference. Okay. So compare the gravitational and electric force on a small dust particle of mass that much that carries a single electron charge. Okay. So here's a dust particle which is carrying a single charge of electron. So the force on it is in this direction. The force on a negative charge is in that direction. And then here's the force of gravity on it. Okay. So they want you to find that. What is the acceleration of the dust particle? Okay, so let's say, we'll choose this direction as positive. So Fe minus mg equal to mass times. Well, actually, first let's calculate Fe over mg. E times E divided by mg. The force on the charged particle is the charge times E. Okay, so this is the magnitude of the charge of the electron. We're just calculating the magnitude of the force. 100 Newton per coulomb. And it weighs 2 into 10 to the minus 15 grams minus 18 kgs into 9.8 meters per second squared. Okay. So this is 10 to the minus 17, 16 times 10 to the minus 18, 16 divided by 2 times 9.8. Okay, so that means the electrostatic force is smaller than the gravitational force. It's 80% of the gravitational force. So the particle would actually accelerate downwards. Okay. And well, why are we calculating this kind of stuff? So if you have allergens in the atmosphere, okay, the faster the allergens settle down to the ground, the less you suffer. But now if this allergen gets charged, it's going to settle down, it's going to hang out in the atmosphere longer. Okay, did you guys understand that? Okay. So what is the acceleration? The acceleration is so mg minus Fe is equal to mass. So instead of accelerating down at this rate, now the acceleration has been reduced by this factor. Okay. Okay, and again, I have not, so the acceleration is 2 meters per second square instead of 10 meters per second square. It's not supposed to do that. So the internet lied to me.